Okay, let's do the example 9.1 on page 255, and I'll read the problem. It says, let us consider the situation proposed at the beginning of this section. A 60-kilogram archer stands at rest on frictionless ice and fires a 0.5-kilogram arrow horizontally at 50 meters per second. With what velocity does the archer move across the ice after firing the arrow? So I kind of drew it up already here, given, find, and solve. Yes, my stick figures are, yeah, they're amazing. All right, and so the arrow is going to, at first has zero velocity, and so does the archer. The arrow goes this way. We want to know with what velocity does the archer go the other way. Now, in this situation, you can consider it an isolated system. And look, yes, there is gravity pulling it down. And by the way, the gravity is going to be pulling the arrow down here very soon, right? But if we look at it, the instant the arrow leaves the bow, we're going to say that the force of gravity is not significantly changed. It hasn't had time to change the momentum of the arrow. The gravity on the archer is canceled by the normal force between the archer's feet and so on. So so we can estimate, we can say, hey, this is an isolated system. In other words, P initial equals P final. So the first thing you have to do is classify the problem. This is a conservation of momentum problem. And that is, it's an isolated closed system, so there's no change in momentum in my system overall. So the amount of momentum I have at the beginning must be equal to the amount of momentum I have at the end. So how much momentum do I have at the beginning? Well, the arrow's not moving, the archer's not moving, nothing's moving. So guess what? I have zero momentum. That's okay. And you say, but wait, the arrow has momentum afterwards. Yes. But remember, momentum is a vector quantity. So the momentum of the archer is going to cancel it out. But we can say, hey, I decided to call the archer object 1 and the arrow object 2. And so I'm going to say this is equal to M1 V1 final plus M2 V2 final. Little vector arrows on there. And what we're trying to find is V1 final. So let's solve for V1 final. V1 final is equal to negative M2 V2 final. Just put that over there. Divided by M1. And so now we have, now I can plug in my values. Negative, what is M2? Half a kilogram. What is V2 final? It's 50 meters per second. And I'll just go ahead and say in the I hat direction. We're going to divide that by M1. The mass of my archer is 60 kilograms. And you do all that arithmetic, you get V1 final is equal to 0.42 meters per second in the negative I hat direction. Negative I hat. And you put the negative out front. I think that's what the book did. Means it's moving, the archer is moving to the left at 0.42 meters per second in the negative x direction. There we go. Okay. So, big picture, and this is what you should do after every problem. What's the big picture? What's the big idea? In this problem, momentum is conserved. How do you know that? Well, the arrow's moving this way, the archer's going to move that way. There's no other outside forces acting on these objects that are going to change the momentum over the time frame we're looking at. And therefore, this is where you start. If you have a problem where momentum is conserved, start here. And then this lets you write an equation with the pieces that allow me to solve for my unknown. Once you recognize this, you're kind of done with physics. Now you're just doing the math. Recognizing that this is a conservation of momentum problem is where the physics is. So look for that. Look for problems where you've got one object pushing off on another and you're looking at both objects. If there's an interaction between the two objects, then you know, okay, for those two objects, if I add their momentum together, anytime the momentum will be equal. The initial momentum will equal the final momentum. Any questions? Okay, that is all.